So here you can rotate.
Slowly learn to find landmarks to orient themselves towards this object, and then make a decision as to what they see here. So hopefully, yes, get across, find landmarks, and decide. Like an example here with the purpose of the tail would be a landmark for you to understand the orientation of it. So now that I can see the tail, oh, it's not.
Yeah, and that'll be really important in the later procedure too. Here we're giving a choice of 3 probes, and you have to choose which one is generating the image on the left. And all these puzzles can be rotated, so you can take a look from different angles. Okay, next we're going to put multiple complex 3D shapes, and have to choose the direction the probe is coming from again. Here we've turned off the beam path, which adds a little bit of difficulty. Yes, this one's a little tricky. We wanted to strike a balance between having too many puzzles, but also increasing the level of complexity as you progress through the game. Okay, so now we're going to move on to a different exercise where there's an object embedded within the sphere, and you're going to click or double tap onto the sphere, and then you'll be able to move the probe around. It'll follow your finger wherever you touch. And the goal here is to identify which shape is embedded within the sphere. So here we're getting more into that like dynamic aspect of the ultrasound scanning. So now you're able to look at multiple viewpoints and try and figure out key features of these different shapes that allow you to identify which one is inside. We tried to keep it to some easy to identify objects that are common, you find commonly. Obviously, we have the ability to add additional modules to this as well, just kind of continuing to iterate over this.
What we really liked about these was the landmark mapping. So, the shapes that we've chosen here are all those shapes that we are familiar with and that we understand the landmarks of. Like, we know the difference between tests and what makes them this kind of testing. So, looking for those landmarks and then come up with familiar shapes was one of the goals here, which is something that
yeah, like there you can identify the crown on the rook. It's all about finding the right angle to view it from. Okay, for this next section, we wanted to move towards more of a human object that you're scanning over. So we designed this sort of crash test dummy, which we are going to now, we've embedded these different objects within. And these objects are a lot more organic looking. They're no longer just common items you might see. So you really have to take a hard look at them and identify, okay, what's unique about this object? What am I looking for? Because they may be very similar depending on the angle that you're viewing it at. And you can see the probe is going to snap to the surface. And then you see here, Theo has grabbed the green sphere, which allows you to adjust the probe angle. So you can kind of translate over the skin with one motion and then adjust your angle to get a finer view as you get close to it. Yeah.
You can see that we are now trying to get closer to what the real scenario would be like, more organic shapes within a more complex form. So
Does anybody have any questions? Okay.
Yeah, we know.
Feel free to stop us.
Yeah, we have fundamentals chapter, so the next chapter is going to be the actual education. This will be a great place to ask questions or we can go on. Yes.
Is there a like a scoring or something to self-assess, like, oh, which part of fundamental I'm weaker or stronger or?
Great question. Great question. Mostly because scoring is like something I talk about at least 5 times a day with my team in any of our games. This game doesn't currently have scoring, mostly because we sometimes see resistance in some audiences in getting like concrete scores. And it turns out astronauts are one of those target audiences that sometimes are a little afraid of scoring. So we've decided against it. I don't know if you will be at the conference down in Galveston. We will have a booth there, and we have other games that do have scoring systems. If you're interested in how we do that, I would be happy to walk you through some of the other games. Any other questions that were there? Yes.
So as you evaluate it, what is the metrics for success? Obviously, it's performance, is it speed, is it accuracy? How do you gauge it?
Not yet. That will be part of this.
Yeah, that's a great question. So these are all going to be metrics that we're going to be pooling for the eventual efficacy study. But I also wanted to kind of add on to Theo's comment because it also is relevant to your question about the scoring. Although we're not displaying a score on screen, we have the ability on the back end to pool analytics. So from each session per user, we can track how they're playing the game, how quickly they progress through the puzzles, how many incorrect guesses they made before they got a correct guess, things like that. So we can get a measure of how well they've completed each task. And then our goal is we want to tie that back into their performance in an actual ultrasound exam to see if that results in an improvement in their scores.
In fact, yes.
Yeah, of course. So one of the things we also did, so Medtronic, we did a game for Medtronic where they had a patient monitoring system. And a lot of times, patient monitoring systems just giving you alerts. And sometimes clinicians were just ignoring it because they got so used to hearing the sounds. So we built this application and tested them and say, okay, now you see this alert, what decision can you make about that? And we really captured all of that data. What we found afterward is when people play in that scenario, we can create an example where there was like 5 or 6 patient monitoring systems, 5 or 6 different choices. And you compound that and force them to kind of make those decisions. We saw they kept coming back and playing before, and we would score them, and then we would see how well they did the second time, see improvement. So there are things that we can measure, and it's really a virtual sandbox. We can make anything that's desired, but we have a lot of examples already of like going back and playing more because of failure and not doing well. They want to go back and then it's that repeat that we see a lot of results indicated like that.
In fact, all of this is automatically built into all lines. So any session that you're currently playing, you get the early score. You have a backend with below the collection automatic. Any of your any where screen. People who use it, we will use that in that. We'll use that technology.
Comment if I may. Since I'm a co-investigator on actually, you just saw a hypothesis and heard that this will improve actual performance in a real ultrasound imaging scenario, right? So the next phase of this is many of you will probably see or hear an announcement that we're recruiting test subjects with ultrasound experience to actually use this as a means as an intervention to measure the teaching effect. So we are going to take it. We are taking it very seriously, and there are some things that are missing here for a purpose, and it is a linear standardized process also for a purpose to standardize the intervention among those test subjects that will be evaluating for with and without game performance and comparing the results in terms of image collection in real test subjects can. So that will be the next thing.
And we'll touch on that a little more later too.
So Ian, at the end of the module, the place to add some suggestions or comments.
Yeah, so actually today at the end of this presentation, there will be a link. If you have comments or suggestions, we'd love to hear it. Or we have an email address you can reach out to us. We don't have it built into the game, but I would assume as part of our process of the second phase study, there would be an opportunity for the participants to provide their feedback then as well.
All right, ready to move on?
Yeah. Here we're getting into the procedural guide. So here we're going through the IJV assessment, and here first up is the first of our 3D models where we're showing users how to hold the probe. And we had a little bit of iteration around here when Aaron so graciously gave us time to show us how they train ultrasound. He demonstrated how to hold the probe for a self-scanning assessment. So we used that as our guide to model this hand. And so we can allow the user here to drag and rotate it around, so you can see kind of some details, and we've pointed out some specifics of what you want to keep in mind when you're holding the probe. Obviously, there's no one correct way to hold the ultrasound probe, but it's a matter of getting comfortable grip and keeping yourself anchored to the skin. Next, we're going to show the application of transmission material, whether that's gel on Earth or in orbit they use water. So here we're showing the application of that. And this next step is going to be a demonstration of how to place the probe on the neck without applying too much pressure, because that could collapse the IJV and affect the quality of image. So just focusing on the fact you just want to maintain contact. You don't want to put too much pressure. Okay, so next is the scanning portion. And once you've played through any of these sections, you're able to go back through and repeat them as necessary if there's a section you're a little more unsure of. So the first step here is a review of all the relevant anatomical landmarks. This is another one of the 3D models we built. Here we've identified 6 of the common landmarks you're going to be looking for in this area to do the IJV scan. And as you rotate the model around, these different waypoints will light up. As you click on them, they'll show that they've been selected. We have a little pop-up that gives you a little bit more information about each section. Okay, and now the 2 main targets here, the IJV and the CCA. This kind of gives you an idea of what you're going to be aiming at when you do the actual scan. Okay, so here's the first time we're letting you scan through a more representative human anatomy. You can move the probe all around this the area shown on screen, so from the chin or jaw down to the clavicle. When you scan the probe over the IJV, it's going to show up with a circle, give you a little call out there as to what we're looking for. Just another reminder about probe orientation, because we feel that's really important to get across. You can see in the simulator itself, the carotid artery is pulsatile, so we added that in to give it a little bit more of like a lifelike representation. Here we're showing a demonstration of what happens when you apply pressure to the probe, so the IJV starts to collapse. Yes. And then next we're going to cover the Valsalva maneuver. And this is going to expand the IJV. See how that looks on the ultrasound as well. So this is meant to be like a procedural guide where you're going to be practicing doing these maneuvers as you're going through this. Next, we're going to teach how you should be breathing while you're performing the assessment. So we have a little timer down at the bottom, and you're going to be instructed to breathe time. This is kind of just a practice and a reminder that you shouldn't be holding your breath. You should just be breathing normally while you're doing the assessment.
Of how we can do more companion guides. So if you ever wanted to say, refresh your memory or have something up with you while you're doing either to breathe along with, we can right, this is an example. So sometimes, we can make games in preparation for procedures, and sometimes we can make companions that you can play around with or follow along with that give you guidance.
Okay, so for the transverse sweep itself, we made this a little more interactive. So you are going to be placing your finger on the screen and following the moving circle to kind of get your timing down correct.
The timing.
Yes. And you can see the ultrasound render also will change, and you can see how by following the path, you'll be keeping the IJV centered and in view. For this interaction, it'll be able to tell if you've gone too fast, too slow, if you've moved off of course, and it'll give you feedback as you go through and as you practice. We're anticipating to get a lot of good metrics here based on how users are accomplishing this path and how that translates to their performance in the actual ultrasound assessment. And you can notice as we're going through these different steps, we're again increasing the difficulty. So we've turned off the timer, we've turned off the guide, and we've also introduced the ultrasound image so you can watch how that's changing on the left as you're following the path. It's tricky.
I can do it.
There you go. Nice. With all the pressure. Okay, so that's the transverse section. Now we're going to move on to some additional scans, which are going to end up being part of the procedure that we're testing for the phase 2 study. First, we're going to do a review of the transverse scan. So there's a little indicator, you're moving the probe to position. And just reviewing that, how that scan is going to look. Now we're going to find our position to do a longitudinal scan. Here we're going to rotate the probe to align the IJV across the screen. This is a sort of on-screen indicator showing that at this point you're meant to take a recording of the longitudinal view. Now we're getting back into longitudinal view. We're going to turn on color Doppler. So this is the representation of what to expect when you see color Doppler. Drag the parallelogram onto the screen, and you'll see the color on screen afterwards.
The scan simulation templates are designed in a way that use figure guide and as a follow along.
And lastly, we're going to cover spectral Doppler. Here you're moving the target into the correct location, and you see a spectral plot underneath. All right. So that completes the procedural section, and just in time. So now we're getting into the image quality assessment. This is more of a quiz or like a sorting game where you're going to be shown these images, and then as you see Theo's labeling, first choosing the correct image, the one that is the highest quality, and then dragging labels to indicate why the other two images were incorrect. So this is meant to be intuitive. You're able to click on the different images and see which one is incorrect and which one is correct. But as you go through that process, you'll be able to understand what it is we're looking for. We've also provided hints if you tap on the question mark icon that can help you give you kind of a tip on what we're asking you to look at here in this image. So here the spectral target is a little off angle and not centered.
What's your passion about this particular chapter? Because I feel like a unique opportunity for a game to provide the ability for you to review scans and load images before you see it, and not only see them, gain more experience with it, but also argue for why something is better or worse, giving us an opportunity to basically tell our audience, our players, what to look for and self-learn how to assess themselves and how to assess their homework when they do it.
And we felt like that was something that was really key to the traditional classroom learning, where if you're going to be scanning yourself, you'll see like a lot of not so perfect images. And we wanted to also be able to represent that in the game. So you get an example of, okay, here's what to look for, here's what not to look for. Yeah, so you've got the feedback, so you're not going to get stuck for too long. Here's an example of a color Doppler image. So, I'm sorry. That's the hardest one. All right. So yeah, that concludes the demonstration of the game. And yeah, obviously meant to be played again and again, used as a sort of refresher. So at this point, I'm going to talk a little bit more about the kinds of tech that we've developed to show the ultrasound and to kind of build out the game itself, the different modules that you saw today. Okay. How did we build the ultrasound simulator? So what we really wanted to focus on for this game was we wanted this to not just simply be you playing a video of an ultrasound scan. We wanted you to have a little bit more freedom of movement, which I hope came across when we played the game. We also wanted to make sure that level of frequency was present. And so what we did was we developed and we kind of iterated on and improved on our past ultrasound simulator that you saw in some of the previous projects that we discussed. What we did for this iteration was the simulator can be thought of as kind of two components. There's the three-dimensional anatomy, which is essentially a volumetric data set of an anatomical image. And then there's the physical model, which is simulating the propagation of ultrasound waves. And what we did to generate the 3D anatomy, which we also call the domain space, is we took an image set of, you can see here we're scanning through this image set. This was freely available online, developed by the NIH. And what they did is they spliced the human cadaver at several sub-millimeter increments, and then took high resolution color photography and paired that with CT and MRI scans. We were then able to import this image set into our game engine and turn it into a volume. And then within that volume, we're able to go voxel by voxel. And to each voxel, we can assign values of acoustic impedance, attenuation, and coefficient of backscattering. What that does is that then informs the physics generator to tell you kind of how the 3D anatomy would look if it were to be interrogated by ultrasound waves. So, as a sort of demonstration of what that kind of propagation looks like, on the back end of our physics engine, you can see here simulated the propagation of an ultrasound wave through an example 2D data set. So you can see the reverberation of ultrasound waves as it passes through and becomes scattered. And that's what's on the back end, generating the ultrasound images that you saw when you completed the game demo. Then we wanted to go through and also improve upon how accurate and representative the ultrasound images that you see are represented and compared to like actual medical ultrasound imagery. So in order to do that, we needed some form of a ground truth. We took a calibration phantom designed for ultrasound calibration, and we scanned that. And that calibration phantom had several different regions which are of known echodynamic values. Then what we did is we built that calibration phantom in engine, and we cast our physics simulator over it as well. So that allowed us to compare what does the image generated by an actual ultrasound look like compared to our control calibration phantom in our engine. And that allowed us to finely tune how the intensity of the pixels that are being returned by the simulator matches what an actual ultrasound would do. By doing this, now we have a really great representation of what ultrasound looks like across a wide range of applications. So, for example, here we're varying the frequency, and you can actually see the visibility of the different calibration dots show differently at different frequencies, meaning like true to life, where you're able to see further depth if you set the simulator to a lower frequency, and vice versa. We felt like an important component of a real-looking ultrasound image was to represent the speckle pattern that you see. So we took some ultrasound images of the calibration phantom again at a high magnification, and we used that to get a really good look at what that speckle pattern is actually looks like. And we were able to then, you can see on the right, our recreation engine accurately represents what that speckle pattern looks like. It's not necessarily going to show a sharp-edged circle. There's going to be some noise that you come to expect when you're doing ultrasound imaging. This is getting into a little bit more additional applications here for other types of ultrasound training. So we're able to fully alter the field of view of the ultrasound beam. So in the scanning simulation, you saw it was representing a linear probe, but if you'd like to do, for example, echocardiography, you could change it to have a curvilinear representation and a further depth of view. We could adjust the bounds of our field of view in any way to represent different ultrasound probes. When you saw the carousel of different types of probes, we had actually programmed the beams of those different ultrasounds to be representative of a common frequency found in each probe type and a common field of view that you would expect for each probe type. So hopefully in the future, we'd be able to demonstrate the need for choosing the correct probe or the correct setting in order to visualize the specific type of anatomy that you're looking We built in some time gain compensation, so you're able to adjust that as you would on an actual ultrasound probe to visualize things further down in the field. And then lastly, we took several example